It is 2025, September 16th, approximately 7:56 a.m. And we are going to continue along the exercises from 3.3. So where was I? Yeah, so the video, my device here, my phone, my camera, ran out of storage while I was in the middle of it, so here's what I'll do. I'll go ahead and just start over on 3.3-3. So that way it's like, you have one continuous thing. Because I could have just started where I left off by saying that, this thing is bounded, but let's go ahead and start right back with it. So use equation 3.14 or other means to show that open parentheses n plus little o of n close parentheses to the k is equal to theta of n to the k for any real constant k. Conclude that the floor function of n to the k is equal to theta of n to the k, and ceiling function of n to the k is equal to theta of n to the k. So as I said earlier, which I'll say now, intuitively speaking, adding little o of n to n means adding something much smaller than n itself. When you raise, open parentheses, n plus little o to the n to the kth power, let's say, the lower order term contributes only lower order growth compared to n to the k. So open parentheses n plus little o of n to the k, close parentheses to the k, grows at the same rate as n to the k. So for floor and ceiling, the difference from n is at most 1, which is negligible compared to n for large n. So let's discuss that a bit more rigorously. Let's say let epsilon of n equal little o of n, so that epsilon of n over n approaches 0 as n approaches infinity. Then open parentheses n plus epsilon of n close parentheses to the k is then equal to n to the k open parentheses 1 plus epsilon of n over n close parentheses to the k. So they don't mention explicitly whenever they have the problem written down there, but equation 3.14 is simply this, that for all real x, real, we have 1 plus x is less than or equal to e to the x. This is by 3.14. That's equation 3.14. And also, if we rearrange this, 1 plus x is greater than or equal to 0 when x is greater than -1. Since epsilon of n over n approaches 0, with our conditions, by our assumptions, factor, which is what, the problem assumes as well. So it's not just us saying, let's cast this thing to the wind. It's that the problem itself sort of depends on that in order to really make sense of a thing. So because we're looking at asymptotic behavior. So this as n approaches infinity thing is necessary to the case, studying all of this in general. So we're assuming that general thing, so we can say since epsilon of n over n approaches 0, the factor of open parentheses 1 plus epsilon of n over n, factor, close parentheses to the k, is bounded above and below by positive constants for large n. Therefore, open parentheses n plus epsilon of n, close parentheses to the k, is equal to theta of n to the k. All right. Let's go on to the next bit here. Not sponsored by Monster Energy drink, but my goodness, that is good stuff. Anyhow, let me erase this so we can proceed with the rest of it. Okay. So we have that the factor, as we mentioned, is bounded. We have the equivalence. Oh, goodness. Now, for floor function of n, we have n minus 1. It's less than or equal to the floor function of n, which is less than or equal to n. Now, raising to the kth power for n greater than or equal to 1, we have open parentheses n minus 1 to the k, n minus 1 close parentheses to the k is less than or equal to the floor function of n to the k, which is less than n to the k. Now, since open parentheses n minus 1 close parentheses to the k is equal to n to the k times open parentheses 1 minus 1 over n close parentheses to the k is equal to n to the k times theta of 1, by the same reasoning above, as above, we conclude floor function of n to the k is equal to theta of n to the k. All right. Now switching the inequalities here for ones more befitting. More befitting ceiling function this is where I kind of do a bit of hand waviness because I'm not explicitly showing it, but that gives that the ceiling function of n is less than or equal to n plus 1 implies that the ceiling function of n to the k is equal to theta of n to the k, right? It said to show, and I feel like we've done that with admittedly some leeway insofar as the rigor is concerned towards the end. But I mean, it's not as though the rigor isn't already implied and encapsulated with this statement, right? So let's go ahead and continue to 3.3-4, which requires even more equations, which they don't include in that exercise part, but which are included earlier in the book. So. Oops, okay. (3.3-4). Prove the following. For part A, we have equation 3.21, which I'm just going to list here because they refuse to. No, but a to the log base b of c is equal to c to the log base b of a for a, b, c greater than 0 with b equal to 1. Not equal to 1, not equal to 1. Okay. So that's the first part. Now what's the second part? Well, equations 3.26 all the way to 3.28, which they also don't list, which I will list here, at least right in the exercises portion. So n factorial is equal to little o of n to the n. Okay. Now what else? 3.27. N factorial is equal to little omega 2 to the n. 3.28 log of n factorial is equal to theta of n log n. And here's a final bit, which is C, part C. So log of theta of n is equal to theta of log n, which is interesting. Okay, so that's what we have for exercise 3.3-4. Now, intuitively, taking logarithms turns exponents into products, right? So the expression a to the log base b of c is symmetric in a and c once written with natural logs. So the two sides must match, at least for a. So what I'll do is I'll state the intuition, and then I'll go and look at it a bit more rigorously for each part. Okay, now let's get on with it. Now, okay. So let's let y equal a to the log with base b of c. Okay, now taking taking base b logs, let's see here, taking base b logs and using log with base b of x to the k is equal to k times log with base b of x. Well, we have that the log with base b of y is equal to the log base b of a to the log base b of c, which is equal to log base b of c times, open parentheses, log base b of c, close parentheses, times, open parentheses, log base b of a, close parentheses, is equal to log with base b of a, log with base b of c to the log with base b of a. Now, since log base b is injective, we can say, okay, y is equal to c to the log base b of a. Therefore, 3.21 holds, right? So we were trying to prove, right? We were trying to prove a to the log base b of c is equal to c to the log base b of a, right? And that's exactly what we got by taking the logarithm of logarithm base b of y, which was this part, to get this part, right? So now let's proceed to b. All right. So for part B, the intuition is this. For n factorial is equal to little o of n to the n, compare each factor of n factorial to n. Now, for n factorial is equal to little omega of 2 to the n, at least half the factors in n factorial are greater than or equal to n over 2. This gives us a huge lower bound that outgrows to the n, 2 to the n. So, and furthermore, for the log of n factorial, Stirling's approximation shows that the log of n factorial is n log n up to lower order terms, right? So let's look at that a bit more rigorously. We'll start with the first one, right? So that's, which by the way, it's just such a underhanded move, right? It's like, not only is it not, it's like, it's one problem, but it's got two parts. And one of those parts actually has three parts. Aren't we, aren't we cool? It's like, oh my gosh. Anyhow, n factorial is equal to little o of n to the n. That's the part we're going to be looking at. We'll move on to the other parts in sequence. So for n is greater than or equal to 1, each term in the product satisfies k is less than or equal to n. Hence, so n factorial is equal to 1 times 2 times, the usual, times n, which is less than n times n times n times n times n times n, all the way to times n, which is equal to n to the n. All right? So what else can we say here? Well, moreover, n factorial over n to the n is equal to the sum from k is equal to 1 to n of k over n, which is equal to the sum from k is equal to 1 to n of open parentheses 1 minus n minus k over n, close parentheses, which is, in fact, less than or equal to the summation from k is equal to 1 to n minus 1 of k over n, which is equal to, open parentheses, n minus 1, close parentheses, factorial, all of that over n to the n minus 1, which approaches 0 as n goes to infinity. A lot of notation, but all of this is to say, so n factorial is equal to little o of n to the n, which is what we wanted, and by definition it fits the strict, does it fit the strict inequality of little o? Can it ever be equal? Let me think about that. Just to make sure. Okay. Well, no. Okay. So this is to establish that the, how do I say this? Let me think about this. So intuitively, right, so the bigger and bigger this thing gets in comparison to this thing, right? So the bigger the relative distance in between this one's highest value, the denominator's highest value, and this one, and the numerator's highest value, leads the entire thing to be equal to 0. Now, if as n approaches infinity, which is what we were looking at here, we get this entire thing to be approaching 0, what we can then say is that, so I think there might be a better argument. There might be a better argument, which is like that, that the difference in between these two. No. That this is some sort of positive number, that this is actually positive, that this is greater than 0. That's what we want. We want the case in which this is always greater than 0. So this may not be the best of proofs for that. Let me think on this a bit. But then again, it's like, well, okay, we're not saying that, what are we saying? Well, it's like, So say I set n equal to 0. Well, oh, no. For n is greater than or equal to 1. So the base case is n is equal to 1 in this case. So we have 1 factorial, that's equal to 1. 1 to the 1 is equal to 1, right? So in which case that would actually be equal to... Okay, I need to think about little o. I need to think about little o to the of n to the... Is it the case that it is strictly so? Okay. Let me think. I mean, but okay. But n factorial is bounded above. N factorial, something with a n factorial, it is fair to say that it is bounded above by n to the n. I don't know about it being little o because that's strict inequality, right? So let me think about this. Because it's not the case that it's always that n to the n is... Unless I'm leaving something out here, right? So it's not the case that n to the n is always greater than n factorial. So, but does n to the n factorial always act as an upper bound to n factorial? And it's like, well, okay, we've proven that to be the case in a way, because the highest it can ever go is n to the n, right? So that's sort of the mesh of a way that I can make it out right now. Though, again, it could be looked at more rigorously. I'll stick with this for now. Keep in mind, there is a lot more rigor that could be said about this. And I think it does kind of... Let me see. If I think in terms of a strict definition. No, I'm not going to dwell on it too much, at least for now. There's more to be said on it, though. So for the next part, n factorial is equal to omega of 2 to the n. That's what we have to set out proving. So for this one, for n is greater than or equal to 2, let me think. Well, I've already discussed the intuition of all of these in an extent. So because I did that whenever I mentioned the intuition for all of it in general, but let's just go right into it then. So for n is greater than or equal to 2, the last, let's say, well, the last floor function n divided by 2 factors of n factorial are at least, that's the key. Because if you say, like, okay, there are at least these, that's only a bit of a step away from saying. It's just that the equality thing is the key, and that's what I'm having a bit of trouble with. So if I look back on this and I say, like, I see, like, okay, because I wish I would have had in my notes like the definitions of each of these things written right in front of me, because I didn't do that when I really probably should have, right? So that's what we're working with here anyhow. But, you know, correct me if I'm wrong, of course. Go in there and take a look at it, you know. So, but for now, for n is greater than or equal to 2, the last floor function n divided by 2 factors of n factorial are at least n divided by 2. So n factorial is greater than or equal to n divided by 2 to the n divided by 2, to the floor function of n divided by 2. So from there we can say, okay, therefore n factorial over 2 to the n is greater than or equal to open parentheses, n divided by 2, close parentheses, to the floor function of n divided by 2, all over 2 to the n. And this, of course, is less than or equal to n over 8, open parentheses, n over 8, close parentheses, to n over n over 2, yeah. So because we're using the n is greater than or equal to 2. So, and this approaches infinity as n approaches infinity. So n factorial is equal to little omega of 2 to the n. That sort of establishes it right there. I guess it's like, well, so for the perspective of asymptotics, of looking at asymptotics, this suffices. But if we were going to be looking at these things a bit more rigorously, we'd go and we'd look at, okay, we'd look at definition this, right? And then we'd say, okay, by the definition, such and such and so and so. We don't necessarily need to do that, though if you wanted to make a stronger case, you could definitely do that. Makes me a bit uncomfortable, but that's par for the course whenever you're looking at things, whenever you're trying to look at things as they are without the most rigor you can possibly do. So, suffice to say, let's just keep it that way for now. Now let's go on to the next part, which is we wanted to show that log of n factorial is equal to theta of n log n. So by Stirling's approximation, which by the way is a different Stirling than the one with the engine. Turns out they're both Scots, but they're not actually closely related, which I think is interesting. And I think the one that came up with the engine, actually, he's a bit closer to our time than the one that came up with this approximation, which is also very interesting. Because I wouldn't think that, because I think like the one that's work is used for computer science, he's obviously going to be closer to our time than the one that came up with the engine deal, but don't believe that's the case. So by Stirling's approximation, we have that n factorial is equal to the square root of 2 is equal to the square root of 2 pi times n times open parentheses n over e close parentheses to the n open parentheses 1 plus theta of 1 over n close parentheses. So that's by Stirling's approximation. Now taking base 2 logs of this, log of n factorial is equal to n log n minus n log e plus 1/2 log n plus theta of 1, which is equal to theta of n log n. So this one's a bit more clear-cut, right? Because we don't have to deal with the sort of, well, the very clear but very small difference of strict inequality versus inequality. So this proves 3.28, right? So we can move on to the third part, which is part C. So intuitively, well, let me restate exactly what part C was about, right? So we want to show that the log of theta of n is equal to the theta of log n. That's what we want to show. Now, if a function is within constant factors of n, then its logarithm differs from log of n by only an additive constant. So let's let f of n equal theta of n. Well, then there exists constants c sub 1, c sub 2 greater than 0, and n naught such that c sub 1 times n is less than or equal to f of n, which is less than or equal to c sub 2 times n for all n greater than or equal to n naught. Taking logs, for n greater than or equal to n naught, we have that the log of c sub 1 plus the log of n is less than or equal to log of f of n, which is less than or equal to the log of c sub 2 plus the log of n. So the log of f of n is equal to the log of n plus theta of 1, which is equal to theta of log n. Therefore, the log of theta of n is equal to theta of log n. So let's think about this. Make sure that this is all clear. Okay. Every step seems to follow in it's lockstep. It's very good. Okay. That's it for 3.3-4. Now let's move on to 3.3-5. Okay, so this one asks two questions. Is the function, ceiling function, log of n factorial, polynomially bounded? And also, is the function ceiling function log of the log of n factorial polynomially bounded? So intuitively, well, factorials grow extremely fast, right? So taking a factorial of log n already beats every power n to the k, because its log is log of n, okay. Because its log is, open parentheses, log of n, close parentheses, times log of the log of n, which eventually exceeds k times log of n. So, but a factorial of the log of n grows much more slowly. Its log is, open parentheses, log of n, close parentheses, times the log of n, which is equal to little o of log of n. So it stays under some polynomial n to the k, which, reminds me, that's why it works. That's why it works, that earlier proof where we didn't exactly look at strict inequalities. It's because with big O, it's like, oh, okay, it does pass eventually, but generally speaking, it will not. For little o, it's like, no, it will never pass this line. It might touch the line, right, but it will never pass that line, I think, is the way that it goes. Correct me if I'm wrong on that, but I think that's the crux of why the argument that I laid out before works. At least on first glance, my first glance, which is why, I included it in the notes. But, we'll see. We'll see. So, but anyhow, back to this question. Now, let's look at this in reference to Stirling's approximation, right? That's pretty key here. So Stirling's approximation says x factorial is equal to the square root of 2 times pi times x times, open parentheses, x over e, close parentheses, to the x times, open parentheses, 1 plus theta of 1 over x, close parentheses. Yeah. And taking base 2 logs yields well, as x approaches infinity, that the log of x factorial is equal to x log x minus x log e plus 1/2 log x plus theta of 1. Now, that itself is, let me think about this. Okay, so let's work with this. So let's let x be equal to the ceiling function of log n, which is equal to log n plus big O of 1. Let's keep this in mind. I'll star this. I'll make this star 1, star sub 1, well, asterisk sub 1. Sort of keep that in mind. I'm going to have to erase the board for more space anyhow, so. Okay. Let me check this to see how many we've got left, because I think we've got quite a bit left to go. It's just, I don't know. I'll have to make this a 3-parter. Gosh dang it. Because I've got some other things I got to attend to. But I think I can knock this one out real fast. So we let x equal to the ceiling function of log of n, right? That's where we were, and then log of n plus big O of 1. So by asterisk 1, log of open parenthesis, well, log of the ceiling function of log of n factorial. Well, that's equal to x log x minus x log e plus big O of log x. And that itself is equal to open parentheses log of n close parentheses times log of n minus open parentheses log of e close parentheses times log of n plus big O of log of n. Now, for any fixed k greater than 0, we're trying to subtract that, which is the argument I was sort of looking at earlier there. But anyway, for k is greater than 0, let's say we have that log of the floor function of log of n factorial minus k of log k times log of n. Well, that's equal to open parentheses log of n close parentheses times open parentheses log of n minus the log of e minus k plus little o of log n. This approaches infinity as n approaches infinity. So and this is because, well, let me now, from that, what can we say? Well, we can say, okay, so ceiling function of log n, that factorial, this eventually exceeds n to the k for every fixed k, for every fixed k. But what does that mean in turn? Well, by definition, the ceiling function of log of n factorial is not polynomially bounded. I'm just going to say polybounded because I'm out of space. But you know what I mean. Right? Okay. Now let's proceed to the next part of this problem. So let's say we have part 2. Right. So okay. How many times do we have to slow this down via logarithm in order to get it polynomially bounded? That's sort of what it looks like. But so let's let y equal the ceiling function log of n, which is equal to log of n plus big O of 1. So by asterisk sub 1, log of the ceiling function of log of n, that factorial, well, that is equal to y times log of y minus y times log of e plus big O of log of y, which in turn is equal to open parentheses log of n times, so many logs, you'd think we're lumberjacks, log of n plus big O of log of n. Therefore, what can we say about this? Well, log of the ceiling function of log of n, that factorial, over log of n is equal to open parentheses log of n, close parentheses, times log of n plus big O of log of n, all over log of n. Now, this approaches 0 as n approaches infinity. Which, by the way, it's like the reason we didn't do that earlier for the other one is like, well, we would have gotten that case for like 0 over 0. Well, actually, let me think about that. Okay, so no. Oh, okay, so here, in this case, there exists a constant k greater than 0 and n not, such that for all n greater than or equal to n naught, log of ceiling function log of n, that factorial is less than, it's bounded by something here, which we can actually state, versus the other one, it's like, well, we had this over here, and it's like we showed that, okay, even if it were the case that you subtracted k log n from it, it's like it's still going to approach infinity. You have accomplished nothing, right? So, but with this being the case, we have that is to say log of n, that factorial is actually less than n to the k. So log of n, that's polynomially bounded. So how many logs does it take in a in the factorial of a ceiling function? 2. 2 logs. 2 polynomially bound n to be polynomially bounded. Let's see. Yeah, because we wanted to show that this bottom part outgrows it, right? Adding some constant k isn't going to really change that, because the bottom part outgrows the denominator outgrows the numerator as n approaches infinity. So that's why we could say that, and it's why we could say that in the previous proofs, and why we didn't need necessarily it to be the case that, okay, subtracting these two things gets you to 0. Bit of a brain fart in a way, but that'll happen. Okay. Now, what do I have time for? Do I have time to look at this one? Don't believe I have time to look at this next one in earnest, which, no, it's good for Ernest because he doesn't have to be looked at too closely, but no. But we'll go ahead and pause this here for now, and we'll pick up with the rest of the 3.3 exercises in the next one, right?